Plasma cutting, definition, history, process, applications, advantages and disadvantages. A stream of ionized gas heated to temperatures above 20,000 C is used in plasma cutting or plasma arc cutting to melt and expel material from the cut. An electrode, cathode, and the workpiece come into contact with electricity during the process, anode. The small, high-temperature, high-velocity plasma jet forms when the arc is constrained by the electrode's recess in a water or air-cooled gas nozzle. The process occurs, and the gas returns to its natural condition when the plasma jet strikes the workpiece, producing gray heat. Typically, argon/hydrogen, or nitrogen are used as plasma gases. For cutting carbon manganese and stainless steel up to 20 mm thick, compressed air makes this type of plasma process extremely competitive with the oxy-fuel technique. Numerous electrically conductive alloys, such as plain carbon and stainless steel, aluminium alloys, nickel alloys, and titanium, can be cut using a plasma arc. The technique was initially created to cut materials that the oxy-fuel process could not sufficiently cut. The plasma torch is often moved while the component or sheet being cut stays stationary. Furthermore, it is typical to attach multiple plasma torches to a cutting table due to the inexpensive cost of the plasma torch compared to the manipulation equipment. Utilizing specialized equipment, plasma cutting can also be done underwater. A significant advancement in plasma arc technology is high-tolerance plasma arc cutting. History of plasma cutting. In the 1960s, plasma welding gave rise to plasma cutting, which later became a very productive method for cutting plates and sheet metal. Plasma cutting produces precise cuts and does not produce metal chips like conventional metal versus metal cutting. The first plasma cutters were huge, expensive, and slow. They were, therefore, mostly employed in mass production mode to repeat cutting patterns. From the late 1980s through the early 1990s, the plasma cutter utilized CNC, computer numerical control, technology, just as other machine tools. However, CNC plasma cutting machines were often only capable of using 2 axes of motion to cut designs and pieces from flat steel sheets. The process of plasma cutting. The plasma cutting technique uses a sustained stream of heated plasma to cut through electrically conducting materials. Steel, stainless steel, aluminum, brass, copper, and other conductive metals are common materials cut with a plasma torch. Manufacturing, vehicle repair and restoration, industrial building, salvage, and scrapping use plasma cutting extensively. Cutting using plasma cutting is unique because it uses conductive gas, which may reach temperatures of 30,000 C. An arc develops in the gas between the workpiece and an electrode close to the gas nozzle. An electrically conductive plasma channel is produced when this electric arc ionizes a portion of the gas. This plasma generates enough heat as the cutting torch current passes through it to melt through the workpiece. In addition, a significant portion of the compressed gas and high-speed plasma blow the hot, molten metal away, separating the workpiece. For both thin and thick materials, plasma cutting is a reliable method. Steel sheets up to 38 mm thick can often be cut using hand torches, but 150 mm thick steel can be cut with powerful computer-controlled torches. To cut and weld sheets in curved or inclined shapes, plasma cutters create a highly hot, localized cone for the cutting process. Step 1. Pilot arc initiation. A start instruction causes the power supply to produce up to 400 VDC of open circuit voltage, also known as no-load voltage, to start the operation. Step 2. Main arc generation. Step 3. Localized heating and melting. As the ionized gas and main arc pass through the nozzle aperture, the nozzle restricts them, increasing the energy density and velocity of the plasma. Step 4. Material ejection. Step 5. Arc movement. The plasma arc is manually or automatically pushed across the workpiece's surface to generate the entire cut after localized heating, melting, and vaporizing have begun. Plasma cutting applications. For thin metal processing, factory upkeep, agricultural upkeep, welding repair shops, metal service shops, trailer production, and artistic endeavors, workshops typically use manual plasma cutters. Cutting tables are frequently used with mechanical plasma cutters, typically much larger than manual ones. Advantages of plasma cutting. Cutting of all materials that conduct electricity. Outstanding performance in mild steel thicknesses of small and medium. Rapid cutting rates, up to 10 times higher than with oxy-fuel. Cutting of medium and large thickness high alloy steel and aluminium materials. Low heat exposure and low noise levels are possible when plasma cutting underwater. Cutting of structural high-strength steel with less heat input. The preparation of premium blanks for medium and thick gauge sheet metal. Disadvantages of plasma cutting. Limitation on the usage of up to 120 mm for underwater cutting and 160 mm, 180 mm for dry cutting. More expensive than cutting methods using oxyacetylene. Dry cutting may cause noise growth. Comparatively high power usage. Lasers provide even better cutting quality. Thanks for watching.